I suppose we've got a fairly quick one for you guys today. Anyways, welcome back. In the last video, we discussed derivatives of vector functions. So now we want to cover integrals of vector functions, which is the next logical step as we try to build our understanding of vector functions in 3D space and how we can perform calculus with them. Now, we aren't in multivariable calculus yet technically, but we are dealing with plane curves or space curves that are still in 3 dimensions. So we are kind of dealing with multivariable calculus. We're dealing with multivariable parametric equations, although we were kind of dealing with that a couple of units ago when we were talking about single variable calculus. Anyways, we will get into integrals now. Integrals are, again, as we discussed in single variable, they're more complicated than derivatives. But I want to preface by saying we've already learned all of the techniques for derivatives and for integrals in our units, Unit 2 and Unit 6 of SVC. So we don't need to go over them again. So in multivariable, what you'll see a lot is that the functions that you need to differentiate and integrate are not going to be super complicated because you've already gone through the motions before. You don't need to do it again. You just need to test your stuff on the new material. So we don't need to keep going back to all the old stuff. Anyways, let's start talking about integrals of vector functions. As you may have imagined, this is very simple. If I want to take the integral between a and b of a vector function r with respect to t, then I just take the integrals by components. I take the integral of f, the integral of g, the integral of h. So I take the integrals, the x component, integral of y component, integral of z component with respect to t, right? And now we can go off of a similar metric to find the integrals of just a function. So like an indefinite integral. If I want to find the indefinite integral of r of t with respect to t, then I'm going to get some capital R, the antiderivative of t, but we need to add a constant of integration. This constant is going to be a vector, right? So we get integral of f dt, integral of g dt, integral of h dt, plus cx, cy, cz. So that should be fairly self-explanatory. And the fundamental theorem of calculus also works in a similar way. If I take the definite integral between a and b of r of t dt, then I evaluate the antiderivative at b, then I evaluate the antiderivative at a, and then I subtract them and I find the difference, and then that's my definite integral. Let's try an example, then we're going to be done. Find the indefinite integral of r of t such that r of t is equal to 2 cosine t, sine t, and 2t. Right? So find the integral of the first function, integral 2 cosine t dt. Take the constant out and integral of cosine is sine. So we get 2 sine of t plus c, or plus c sub x, I guess. Second integral of sine is negative cosine, fairly simple. So we get an integral of sine dt is equal to negative cosine of t plus cy. Then finally, integral of 2t dt is equal to t squared. Use the reverse power rule, plus c sub z. So thus we can determine that the integral of r of t with respect to t is equal to 2 sine t, negative cosine t, and t squared, plus vector constant of integration. All right, now as you may have noticed, it's very hard to determine a real application to this integral of a vector function. It's not particularly useful to us because what are we finding the area under, right? So we are going to postpone taking integrals of vector functions until a little bit later, actually, to deal with them conceptually. But we can use integral formulas like arc length in order to make them useful, because finding the length of a vector function is fairly useful, and also we can use it to incite curvature as well. So what we're going to do is we are going to talk about curvature and arc length in the next video, and then after that we are going to move on to discussing physics of these vector functions. All of physics is modeled by vector functions pretty much. If you think about 2D motion, it's a parametric equation, but it's really described by a vector function. All right, in the next video, again, talking about arc length and curvature. We'll see you guys then. Keep here.